Patrick Wardle presents Working, Enreading, and Staying. Adventures in Hacking Mac OS. Attackers have been targeting Mac users with malicious Office documents, but things could have been a lot worse. Once they have access to a Mac, what can they install? 2020 saw the first two computer virus infecting Macs. Intrigue? Let's tear it apart.
All right, aloha and welcome to my talk, Breaking, Entering, and then Staying. My name is Patrick Wardle. I am a principal security researcher at Jamf and also the creator of the Mac security website and tool suite, Objective-C. So today's talk is kind of broken up into three parts or three chapters. So we're going to start with chapter 1. And we're going to detail recent attacks targeting Mac users. We'll see that these attacks leveraged macro-laced documents, and we're also then going to discuss how we can go about analyzing these malicious documents. We're then going to discuss a document-based exploit chain that I created that combines what was at the time a few zero-day vulnerabilities to bypass the sandbox and Apple's latest security mechanisms. So now we have the ability to hack Macs. The question is, what can we, or attackers, do to maintain persistent access? So in chapter 2, we're going to talk about an intriguing piece of malware that was recently captured in the wild that is perhaps the first true computer virus targeting macOS. And honestly, it would make a rather excellent payload for our document-based attack. Finally, we're going to wrap everything up in chapter 3, and we're going to talk about defense, discussing generic methods for detecting and thwarting both exploits and malware. So let's dive in, starting by looking at how we could hack macOS via malicious macro-laced Office documents. We're going to note some trends, talk about some in-the-wild attacks targeting Mac users, and then discuss a neat exploit chain that was able to fully infect a fully patched macOS system. All right, before we dive in though, what is a macro? So I've added the official definition from Microsoft on the slide, but in short, a macro is embedded executable code in Microsoft Office documents. In other words, it allows one to add code to a document. So here, for example, as we can see on the slide, we've inserted a macro into a Word document that will display a pop-up that says, "Hello World." And we'll talk about this more, but as we've placed this macro within the auto open subroutine, if the user has macros enabled, this will be automatically executed when the document is opened, as we can see on the slide. Now, from a security point of view, allowing executable code to be placed in Microsoft Office documents has proved to be a terrible idea, which attackers have unfortunately abused for years, for decades. In fact, the infamous Melissa virus that targeted Windows systems all the way back in 1999 was, yes, you guessed it, a macro virus. Now, Microsoft, since then, has added some mitigations, such as alerts and sandboxing. But as we'll see, this really hasn't fully mitigated macro-based threats. Now, if you're familiar with macro-based attacks, you probably are familiar with them in the context of Windows-based computers. And this is definitely true. Traditionally, macro-based attacks have targeted Windows systems due to two main reasons. First, macros are essentially a Microsoft creation and thus generally only work in Microsoft products. That is to say, Apple Office applications such as Pages or Numbers don't run macro code. Also, Windows computers, at least in the past, were far more common, far more prevalent, especially in the enterprise. However, this is all changing, especially in the commercial and startup space. Mac computers are everywhere. So in short, there are now more Mac computers running Microsoft Office, which makes a lot more targets for opportunistic hackers. So now let's look at some recent attacks targeting Mac users, focusing on attacks that leveraged macro-laced documents. So first, we'll kind of give a high-level overview of each attack, and then we'll dive into discussing how to extract and analyze their malicious payloads. The idea is really to gain a deeper understanding of these attacks and also to talk about the tools and techniques. So if you come across such a document, you now have the ability to analyze these yourself. So we're going to start in 2017. We have a document whose title makes it appear to be about Trump's rather, unfortunate election victory. And if the document is open, it's really not about the election, but rather something malicious. And so if the users click enable macros, the system will actually become infected because this is a malicious document. Moving on to 2018, we have another malicious document. This one, though, appears to be about Bitcoin, which was a very hot topic at the time. You can imagine if someone sends this document to you, perhaps you might open it. And unfortunately, if you opened this document and allowed the macros to run, your system would be infected. Now, we'll dig into this document a little more, but the most interesting aspect of this attack was embedded exploit code that was designed to bypass Office Sandbox. So this is one of the more sophisticated attacks we've seen. Next up, if we move to 2019, we have a malicious document from the prolific Lazarus APT group. Lazarus group is generally associated with the North Koreans. So this is kind of interesting, mostly because it shows the fact that APT groups are jumping on the, hey, let's target macOS via these macros bandwagon. Again, if the user opens this malicious document, clicks allow to enable macros, the system will be infected. So now let's discuss methods of analyzing such documents, showing exactly how to extract the embedded macros and analyze then this macro code and any payloads. So the first thing is, we obviously have to have the ability to extract the embedded macro code. Now, due to time constraints, we're not really going to get into the low-level details of Microsoft Office documents, specifically their file format. It's really beyond the scope of the talk. But the good news is you don't really have to worry about them anyways. Turns out there's several great tools available to extract embedded macros for you. Awesome. My favorite is a Python package called OLE Tools that's available on GitHub. We can see on the slide, if you download the package and execute the OLE VBA command with the -c parameter, and then give it the path to the document that you think has embedded macros, the tool will parse the document and extract and dump any embedded macros for us. This is great. Also, there are various online websites that you can upload a document to, and if it's malicious and has this embedded code, the website will extract that macro code for you. So now we understand how to extract embedded macro code. Let's return to some of the malicious documents we talked about earlier and briefly discuss and look at their malicious payloads. So starting a document from, I believe it was 2017, we can use the OLE VBA command, and as we mentioned, we can extract any embedded macros. As we can see on the slide, we now have the output from this, and we can see a subroutine in the macro code called Fisher. And this is invoked via the auto-open method. The auto-open method is a Microsoft API, and as its name implies, code within the auto-open subroutine will be automatically executed anytime the document is opened. If and only if, though, the user has clicked enabled macros. So what does this Fisher subroutine do? Well, basically does two things. It first builds a base 64 encoded string, and then decodes and executes this string via Python. So if we manually decode the string, we can see that it's Python code, which is unsurprising because it's being passed to Python to be executed. So yeah, of course it's Python code. So what does this Python code do? Well, basically four main things. So first, it checks to make sure the popular macOS firewall little snitch is not running. Then it downloads a second stage payload from securitychecking.org. 3, it decrypts this payload. And then finally, in step 4, it executes this now decrypted payload. If you've analyzed a lot of these documents, you might think that this code looks familiar, and in fact it does, because it is Empire, which is a well-known open source Python backdoor. And what about the second stage payload? What is it downloading and running? Well, unfortunately, at the time of analyzing this document, that second stage payload was no longer available because the command and control server was offline. But it's likely Empire's second stage payload, which gives attackers full access over the infected system. If we move on to the Bitcoin document from 2018, again, we can use the OLE VBA tool to extract the embedded macros, which we have on the screen. Again, it contains encoded Python. This just seems to be a popular technique used by unrelated adversaries, but it also appears to contain an embedded property list. This is interesting. Why is it there? We take a closer look. We'll first look at the Python code. As I mentioned, it's encoded, base64 encoded, which is luckily trivial to decode. On the slide, you can see we decode this via the base64 library module in Python, which then outputs the unencoded, decoded Python code. I've kind of cleaned that up and put that on the bottom of the slide. You can see it's super simple, just connects out to a server, then downloads and executes a second stage payload. This turned out to be Metasploit's Meterpreter, which again gives remote access to an infected system. Though this attack was unrelated to the previous one, we do see a lot of kind of overlap in the sense that attackers appear to be somewhat lazy and are simply using existing open source payloads to embed in these malicious documents. Now, I mentioned the most interesting part of this document, this attack, was its ability to escape outside the sandbox. So what is the sandbox, right? We've mentioned this a few times. So recent versions of Office run in a sandbox, which means that even if code such as macro code, malicious macro code is executed, it will be constrained. It'll be kind of contained, limited by what it can do. So the sandbox prevents it from doing things like persisting a backdoor, accessing the user's passwords, or doing other nefarious things. From a security point of view, such a sandbox is a great idea. Unfortunately, though, security researcher Adam Chester found a neat way to escape out of this sandbox and posted a great blog post, an article on my website, Objective-C. In short, he found a sandbox exception based on a faulty regular expression, regex, that allowed sandbox code to create specifically named files anywhere on the system. Normally, if you're running within a sandbox, you can't create files in arbitrary locations. That would kind of defeat the purpose of the sandbox. However, he found that via this faulty regular expression, he could create something called a launch agent that exists outside the sandbox. The next time the system was rebooted or the user logs in, this launch agent would run outside the context of the sandbox. In other words, it was a sandbox escape. Now, it's interesting because looking at the malicious code of this attack, we can see the attackers simply went to my website and actually copied and pasted this sandbox escape verbatim. They didn't even change anything from the proof of concept, embedded it directly in their malicious documents, and then sent it out. On unpatched systems, this means if the user opened the document, not only would the malicious macro code run, the sandbox escape would allow the malware to escape out of the constraints of the sandbox and cause more damage to the system. Finally, the last document we talked about, if we extract the embedded macro code, we can see it's fairly straightforward. In this case, it's unencoded. There's no Python, there's no base64 encoding. So it's very easy to understand what it does. Three basic things: simply downloads and executes a second stage persistent implant. If we grab this implant, it is a binary called mt.dat, which turns out to be a pretty standard backdoor created by the Lazarus group adversaries to give them remote continuing access to the infected system. So that's an overview of the recent macro-based attacks against macOS, which gives us a pretty thorough understanding of the current status quo. So now let's talk about a more sophisticated macro-based exploit chain. And the reason we're going to do this is because current macro-based attacks are super lame, almost ineffective, almost useless. Let's list the ways why this statement is true. So first, any of the attacks that we just described when the user goes to open the document, Microsoft Office will generate a big alert, basically telling the user that this document contains macros and that these macros are likely malicious and that they probably shouldn't run them. So the only way these attacks are actually going to work is if the user ignores this prompt and clicks enable macros. And luckily, most users won't. So this means most of those attacks are going to fail out of the box. They're not even going to be able to run. Also, Microsoft patched Adam's sandbox bug, meaning all current attacks remain sandbox. So even if the user clicks on enable macros, the macro code will be constricted again by the sandbox, so won't be able to do things like persist a backdoor or access the majority of the user's files. Finally, at least on Catalina, which is the most recent version of Apple's desktop operating system, due to something called quarantine and notarization, payloads, even those executed in the sandbox, may be blocked. Basically, what Apple does now is say Apple has to bless or validate the code before it's allowed to run. Obviously, they're not going to approve backdoors from running. So this means the current attacks are, as I mentioned, basically useless. So I kind of wanted to see if the problem could be worse. So what we're going to do now is walk through an exploit chain that suffers from none of these limitations. So the exploit chain starts with a neat bug found a while ago by two other security researchers and some researchers at CERT. So I didn't find this initial bug, just kind of the first bug we're going to use in the exploit chain. And the vulnerability they found was that even if macros are turned off, these researchers could create a document that contained macros that would be automatically executed with no alerts, no prompts. So how are they able to do this? Well, it turns out they were able to abuse a really old file format from the 1980s called SYLK files, and using actually an ancient macro languages called XLM. Now, Microsoft loves to support old file formats for compatibility reasons. So yes, these ancient file formats and this ancient macro programming language will actually still work, even today, still supported by Microsoft Office documents, specifically by Excel. So what the researchers found is they could write this XLM macro code. And again, and this is very important, it would be automatically executed, ironically, if the user had set never run macros, which is the most secure settings. The researchers published a great write-up, kind of included a link on the slide. So if you're more interested in that, check out their great research. So I wrote a simple proof of concept based off their bug. And in this little video, we're going to see a malicious document that is downloaded from the internet. We're going to see that when the user goes to open this document, calculator is automatically launched via malicious macro code. And the main takeaway here again is there's no alerts, no warnings. Document is opened, calculator is popped. So download the file, open it, there's calculator. Hooray, kind of neat. Again, no alerts, no prompts, nothing about macros, just popping calc. Now we noted though that Microsoft Office is sandbox, which means sure we can spawn calculator, but that's really about it. We can't persist the backdoor, we can't access users' files, right? That's the point of a sandbox, to block malicious code. So in short, we need a sandbox escape in order to do any real damage. So I started by looking at Microsoft's patch for Adam's bug, and I found that they actually didn't fix or address the faulty regular expression. They simply blocked certain locations, such as the launch agent directory. Meaning, we can still create arbitrary files as long as they start with $, so they conform to the faulty regex almost anywhere. Now, we can't create a file in the launch agents directory, but pretty much anywhere else. And we're going to see that's very important. Now, our goal, of course, is to execute something, a binary, outside the sandbox, so we can persist and do more problematic, more evil things. We just noted we can still write specially named files to essentially arbitrary locations, as Microsoft didn't fully patch that. Turns out, also in the sandbox, via macro code, which is automatically executed with no alerts, no prompts, we can download and execute scripts. We can see this on the slide in our process monitor. Now, these scripts will still be sandboxed, as they are children of a sandbox process, but still it's a start, right? We can run Python code. That gives us a lot more extensibility. So what I found was via a Python script that we can execute via the sandbox, we can create something called a login item. Now, although we can't specify any arguments in this login item, this login item will be automatically started the next time the user logs in. And since login items are started by macOS versus by us in the sandbox, turns out that when they're launched, they're not running in the sandbox. So hooray, we now have a sandbox escape. And we can confirm this by persisting Apple's terminal.app from the sandbox. And then on the next login, as we can see on the slide at the bottom, terminal.app is automatically running. And if we look at the sandbox field in Activity Monitor, we can see that it's set to no, meaning that terminal is running outside the sandbox. Now, we immediately run into Catalina's more stringent quarantine and notarization requirements. So if we persist an arbitrary backdoor as a login item, say a backdoor or something we create, when macOS goes to launch that, it actually sees that it's not notarized or not approved by Apple and blocks it. So this sucks. Right? Another obstacle we have to address. Well, good thing is hope is not lost. If, and this is a big if we can create something called a launch agent, this allows us to specify program arguments, which allow us then to create an interactive, non-sandboxed reverse shell via bash. This is important because this interactive reverse shell is running outside the sandbox. We can download additional items that are not constrained by Apple's notarization requirements. But recall, Microsoft's patch specifically prevents the creation of launch agents. Bummer. So we have all the potential pieces, but we just can't quite put them together, right? So we can escape the sandbox via a login item, but login items don't take arguments. Also, they can't be random binaries because due to Apple's notarization, Apple will block that. So in other words, the only thing we can persist are Apple-approved items, again, with no arguments. And sure, we could potentially bypass the notarization requirements via a launch agent, but we can't directly create a launch agent from the sandbox due to Microsoft's partial patch. So what we have to do is we have to figure out a way for the system or for an Apple binary, again, with no process arguments, to create a launch agent for us. So I had a random idea. What happens if you create a login item that is not a binary or an application? This is kind of strange. I didn't know what was going to happen because normally you create a login item and you set it to an application that you'd like the system to automatically start each time the user logs in. This is what login items do. But what happens if you create a login item that points to a PDF document or a zip file? Well, it turns out on logging, macOS will invoke the default file handler for that file type. Thus, for a PDF, it'll open it in preview. For a zip file, macOS will automatically invoke Apple's archive utility to unzip the file. Now, remember we want to create a launch agent, but due to Office's custom sandbox rule, we can't directly write to the user's launch agent directory. But if that directory doesn't exist, which it does not on a default install of macOS, what we can do is we can drop that zip file one directory up in the user's library directory. This is allowed from the sandbox, right? We're not writing to the directory, we're writing one directory up. And what do we put in this zip file? Well, we put a directory called launch agents. And then within that, we put our launch agent property list that contains our program arguments that will create an interactive backdoor shell out to us that allows us to download additional code. So once we've done this, when the user logs in, the zip file will be automatically unzipped and the launch agent will be created for us. So here's kind of a walkthrough then of the entire exploit chain. Step one, the user opens our malicious Office document. And again, using the initial bug, we get macro code execution automatically. No alerts, no prompt. Now, this code is running within the sandbox, so we have to escape the sandbox. So what we do is we create a login item, which is allowed, that points to a zip file. On the next login, the archive utility is automatically run. This is run outside the sandbox, and also it is allowed to run because it's an Apple-signed process. This extracts our zip file, and since our zip file has a directory called launch agents, it is allowed to create the launch agent directory. On next login, macOS will process any launch agents it finds, which includes our malicious launch agent, runs it, and launches our bash-based interactive backdoor. Again, we're using bash because that's an Apple-signed process, so the system allows it to run. It doesn't have to be notarized because it's part of the operating system. As I mentioned, this bash backdoor is running outside the sandbox, means it can download files. And one of the things it can do, because it's outside the sandbox, it can do something called unquarantine files. This is important because once a file is unquarantined, it is not constrained by Apple's notarization requirements. This is great. So this means we can run our own code. We can run malware. So what did we decide to do? We decided, let's run some Mac malware. Awesome. We can see on the slides, once I finally got this all working, I was pretty stoked. All right. So now we have the ability to hack Macs by simply opening an Office document, right? If you get a user who has Microsoft Office installed to open a document, their system is toast. We're stoked. So what could we, or what could attackers do then to maintain persistent access? Well, really, they could do anything, but I thought it would be neat to focus on some brand new Mac malware. So in this next part of the talk, we're going to kind of transition a little bit and talk about an intriguing piece of Mac malware named EvilQuest. We're going to talk about how to analyze its code to uncover its rather insidious capabilities, and also show how it was perhaps the first true computer virus targeting macOS. Again, this malware could very easily be packaged up with our macro-based exploit chain to be used in very damaging, very evil ways. Now, I first want to give kudos to Dinesh on Twitter for uncovering this malware in the wild. His tweet definitely intrigued me to fully dig into EvilQuest. Specifically, it didn't have any antivirus detections, which indicated it likely was a brand new sample, a brand new specimen. And also, he noted it had some ransomware capabilities, which is intriguing. We don't run into a lot of ransomware targeting macOS specifically. Now, before we dive into the malware to talk about how it persists and what its capabilities are that perhaps we could leverage as a payload for our macro-based attack, we need to do some initial triage because we need to show how to decrypt embedded strings within the malware and also thwart its anti-analysis logic so that we can analyze it comprehensively before we utilize it for our own purposes. So the malware was discovered in a disk image, a DMG file. So the first thing we can do is we can mount that DMG file, and we can do that with the HDI utility command. And we can see it contains a single package called mixedinkey8.pkg. Now, my favorite tool for analyzing packages is aptly called suspicious packages. And what we can do is, via this great utility, this free tool, is we can analyze the package's contents. So we can see that within this PKG file, there's basically two main pieces. There's an application called mixedinkey.app. And if we validate the code signing certificate of this, we can see that it's validly signed by the original developers. So we can likely assume that this is pristine. This hasn't been tampered with. However, there's a second item, which is a lot more interesting. It's a mock O binary called patch, which is unsigned. That's interesting. Let's start there. So if we look closer at the PKG, we can see that part of the installation process, it'll ask the user for their credentials, and then it'll execute something called a post-install script. This is executed after the installer is basically completed and moved all the files into place. So we can see, and we've included the post-install script on the slide, the script moves the patch binary into a directory called mixedinkey, renaming the binary to toolroomd. So let's take a closer look at this patch binary, or as it was renamed, toolroomd. And one of the first things is I often run the strings utility to extract any embedded strings. This can give us a lot of insight into perhaps the capabilities of the malware. And we can see some interesting things based on the embedded strings in this patch binary. We can see something that looks like command line arguments, perhaps some strings related to a command and control server, perhaps something related to file encryption, keylogging, and probably most interestingly, we have a path that if we swap, turns out to be a path that turns into the English word or phrase effective idiot, or EI. And we'll see as we analyze the rest of this malware, they use this EI string a lot. So this is likely the internal name that the malware author gave their creation. Effective idiot, kind of humorous. We can also run the nm utility. This is another utility that macOS ships with, and this can extract embedded symbols and APIs that the malware imports. These API imports can reveal the malware's likely capability. For example, we can see APIs related to capturing keystrokes, so we can assume that the malware has keylogging capabilities. But even more insightful, we can see the actual names of the malware's functions and methods, which is interesting. This is what the malware author has named their code. Again, this gives us a lot of insight into the malware. Now, when I ran the strings command, I did notice what appeared to be a lot of encrypted strings. And this is common. Malware authors will often encrypt sensitive strings because they know analysts, such as myself, are going to run the strings command and try to look at what the malware does. So it's kind of just an extra layer of obfuscation to hinder analysis. What we can do, though, is we can pop into a disassembler, and we can see that these encrypted strings are passed to a function called EI_stir. Again, EI likely standing for effective idiot. I'm kind of lazy, so instead of trying to understand the string decryption routine, I just created an injectable dynamic library that once loaded into the context of the malware would resolve this decryption function and then just invoke it on all of the encrypted strings. So in other words, I let the malware decrypt the strings for me. And we can see these decrypted strings are rather revealing. We can see what appear to be URLs and IP addresses, likely of command and control servers. We also see a launch item property list, a list of security applications, and perhaps ransom instructions. Again, very interesting, very insightful. Finally, during this initial triage, we encounter various anti-analysis logic. We see a function named isVirtualMachine that attempts to detect if the malware is running within a sandbox. And if so, we'll exit. And we also see a function named isDebugging and preventTrace, which seek to prevent successful debugging of the malware. Now, it's important for us to identify these because if we don't, and we try to debug the malware would detect that it's being debugged and exit or kick us out. Luckily, though, once we have identified these functions, it turns out really easy to bypass them. We simply set a breakpoint on the function, and then when the malware is about to execute them, we can change the instruction pointer and skip over them. So this anti-analysis logic is never actually executed. So once we've bypassed the anti-analysis logic of this malware and also decrypted all the encrypted strings, our full analysis can commence. So let's start by discussing and analyzing its persistence mechanism. So persistence in the context of this presentation is the mechanism the malware uses to ensure that every time the system is restarted, the malware is automatically relaunched or re-executed by the operating system. So if we look at the malware, we find a function named EI persistence main. And we can see the malware first executing this anti-debugging logic we talked about, which we'll simply skip over. We don't want it to execute. It also then enumerates all running processes looking for popular security tools. And if these security tools are found, the malware will kill them. This is likely because some of these tools may detect the malware's subsequent actions, so the malware will proactively kill them to make sure they don't get in the way. Interesting. It then invokes a function named persist executable, and via a file monitor, we can observe the malware making a copy of itself. The malware then invokes a method called install_daemon to persist itself both as a launch agent and a launch daemon. So it persists itself twice. If we recall, we talked about this before, but the property list for these launch items was stored embedded, encrypted within the malware. What we can do, though, is we can allow the malware to execute this function, and then we can simply hop into the file system and look at the property list that was created on disk, obviously in a virtual machine. We can see that the run at load key is set to true, which tells macOS, please automatically start the malware every time the system is launched. And then the malware kicks off itself the first time via AppleScript. So now the malware is off and running. So since we understand how the malware persists, let's talk about its capabilities, its goals. The first thing it does is it connects out to look for a command and control server to check in and to ask if the attacker has any tasking for this. So what the malware does is decrypt a hard-coded address of a URL that's hosted on pythonanywhere.com. It then connects out to this URL to look for a file named rec.txt. This file contains the address of the attacker's command and control server. This means the attacker can change, obviously, their command and control server by editing this rec.txt file. Now, if either of these URLs are offline, malware also has a hard-coded backup command and control server. One of the first actions the malware takes once it's checked in is to generate and exfiltrate a recursive directory listing of an infected system. In a debugger, we can watch this in action. We can note that the root directory begins at /users. So we'll enumerate the user's directory listing, upload that to the attacker's server. The malware also searches for various files that match a list of embedded regular expressions that we can see on the slide. From these regexes, we can see that the malware has a propensity for certificates and cryptocurrency keys and wallets. The attacker is obviously very interested in those files. So what we can do is we can test this by creating a file named key.png, for example, on the desktop of an infected system. And then in a debugger, we can observe the malware detecting this file because it matches one of those regular expressions, scooping it up and exfiltrating it to the attacker. So if your system is infected with this, it's likely the attacker has access to all your cryptocurrency wallets and keys. Bummer. The malware also supports a handful of commands to allow the attacker complete and continuing access. We can see on the slide some of the logic in the malware that handles this. Specifically, once it gets a command from the command control server, it invokes a method named dispatch. And I've mentioned or put the commands that the malware supports on the slide, but we can see its basic things like download, execute, kicking off a keylogger. Now, I do want to briefly mention one of the commands, command number 1, which is named react_exec. And this executes a function which the malware author has named ei_run_memory, which executes a decrypted payload downloaded from the command and control server directly from memory. Now, I talked about this technique at Black Hat a while back in 2015 or so. Clearly, though, the benefit is the decrypted payloads never hit the disk. This means they can't be scanned by an antivirus engine or grabbed for forensics analysis. It's a rather sophisticated, elegant technique from the malware point of view. The malware author also supports ransomware logic. Logic is pretty standard ransomware logic. What it does is it enumerates all files on the system that match a list of file extensions. File extensions such as documents, HTML documents, music, essentially the user's files, right? It then invokes a method named carve_target for each of these files. And what this does is it reads the contents of the file into memory, encrypts it, writes the encrypted contents out to a temporary file, deletes the original file, and then renames the temporary file. End result is the original file is encrypted. Once the files have all been encrypted, the ransomware or the malware logic, the ransomware logic in the malware, creates a README text document and also displays an alert to the user. And that's kind of funny because the malware then also reads this out loud. So it uses macOS's built-in speech capabilities. So all of a sudden your computer will start talking to you, telling you that all your files are encrypted. Good news is some research figured out that the keying material that's stored within the encrypted files is actually enough to decrypt the files. So you really don't actually even have to pay for the ransomware decryption. Now I wanted to save the best to the last, what I think is the best to the last. And this is that EvenQuest, this malware sample we've been analyzing, appears to be the first, or perhaps the first, in the wild computer virus targeting macOS. So I have the definition of a computer virus on the slide. And basically, it says that once a virus gains access to a system, it'll infect other files on the system, replicating itself. Most malware, if not all malware that infects macOS, does not do this. So specifically in a background thread, the malware invokes a function named getTargets to get a list of executables on the infected system. And then for each of these executables, it invokes a function named append.ei, EI again being effective idiot. As its name implies, append.ei appends itself into each of these executables. More specifically, it inserts itself into the start of the executable and then adds a trailer that points to the original code. This means that whenever these infected binaries are run, either by the user or by the operating system, the viral code at the start will execute first. Now, to ensure nothing appears amiss, the virus then writes out the original code and executes this. This is not super stealthy, but it has the benefit of restoring the code signing signature of the original file, which must be intact if that original binary contains code signing entitlements. So this ensures that nothing is broken. Interestingly, the malware continues to evolve. Trend Micro recently published a great report on the updates of EvilQuest, showing that it has now improved anti-analysis logic, new capabilities, and interestingly, the ransomware logic is gone. However, the coolest part about this update is in the ping command, which now says, "Hello, Patrick." Apparently, the malware authors read some of my initial work. Honestly, I've always kind of wanted to shout out in a computer virus. I don't know if that's wrong, but I think this is pretty awesome. All right, so we've talked about hacking Macs and a new computer virus that could easily be installed as the payload of this hack. Let's end by talking about defending against these attacks and some generic methods of detections. First up, the vulnerabilities I found. I responsibly reported these to both Microsoft and Apple. Good news is they're now fully patched. So as always, it's really important to always keep your macOS system up to date. So now, how do we defend against these attacks and malware? Well, the short answer is by monitoring and detecting anomalous system activity. And to do such monitoring, we can use Apple's new endpoint security framework. And as Apple states, this is an API, a framework for monitoring system events to detect malicious activities. I've also written some tutorials about this topic as well. So first up, we want to be able to detect suspicious process events. And we can do that, again, using Apple's new endpoint security framework. It's really easy to create a process monitor that can detect suspicious children. We can see on the slide, we can now detect when an Office application, for example, Excel, spawns a child process that is, well, suspicious. Regardless of the reason, if you see Excel spawning curl or Python, that's bad news. Something is amiss. Patrick might be trying to hack your Mac. We can also detect a wide range of attacks, including the exploit chain we described, by monitoring the file system for persistence. Again, using Apple's new endpoint security framework, we can monitor for file events, specifically ones that relate to persistence, such as the creation of a login item. So here, for example, we can see the creation of a login item that is not, in fact, an application, but a zip file. Again, this is very suspicious, and in this case is indicative of the sandbox escape we talked about earlier. Now on to detecting malware. Even now, malware such as EvilQuest is really not that hard to detect if we focus on behavior-based detections versus static signatures. First, it's pretty trivial to detect the malware's persistence. It's an unsigned launch item masquerading as an Apple binary. This is really shady. All Apple binaries are signed. So this is a huge red flag. We can also detect its ransomware logic by detecting the rapid creation of encrypted files by an untrusted process. Again, this is a very suspicious, shady action. Finally, if we're monitoring network traffic, for example, via a firewall, we can detect unauthorized network connections. So either individually or cumulatively, we can use these malicious, the observations of these malicious activities to detect something is amiss and uncover the malware, even if we've never seen this specific malware specimen before. All right, let's wrap this up. So today, we illustrated that attackers are now, more than ever, targeting macOS users, often with malicious Office documents. And while their attacks are rather lame, we created a lovely exploit chain that allowed us to infect fully patched macOS systems. Attackers are also improving their malware. Today, we looked at EvilQuest, a new sophisticated computer virus capable of infecting macOS systems. However, we ended by showing that by leveraging Apple's new endpoint security framework, we can generically detect these and other attacks. Now, one more thing, I'm excited to announce a new book, The Art of Mac Malware. This is a free online book dedicated to all things about Mac malware. So if you're interested, pop over to taomm.org to check it out. I want to end by thanking you all for attending my talk. Hope you're all staying safe and hope to see you all in 2021. I also want to thank Jamf for putting up with my shenanigans and also all the amazing companies who support Objective-C. So again, thank you so much for attending my talk and hope to see you all next year. Aloha.